Hey everyone, Professor Steve here, and we are going to sort of wrap up um, at least the last, for the purpose of this class, the last of the phenomenon that causes upwelling. This is probably the smallest scale version and the most episodic of all those. And remember what I mean by episodic is a little bit more unpredictable. Something that could be caused is not a little bit unpredictably. We sort of know what causes it and how they're caused, but you can't really predict when, and you can't predict how long they're going to last. Okay, just um, but remember the main point of the unit and of looking at eddies in this way is exploring all the main mechanisms for breaking down this barrier, but the stratification between the surface and the deep ocean, pumping the nutrients up to sort of cause primary production. Now, in terms of eddies, where we left off was the formation of eddies from eddy viscosity, and that's when two different fluid media are moving past each other. They cause the friction between them causes turbulence, and these eddies sort of spawn off of them. And what we spoke of was, some will spin off in a counterclockwise motion, with cooler water trapping warm water at the core, at the center of this pressure system, and then how they can also spin off in a clockwise direction with warm water trapping cold water at the center. And we used as an example the Gulf Stream coming up along the eastern seaboard of the United States. Here's New Jersey. Mixing with this cold water that comes in from the north, and where these interact, the interface between these two water masses, we get this buildup of friction, we get this eddy viscosity, we get warm water trapping cold water at its core and spinning off as a low pressure center. We get warm water trapped by cold water and spinning off as a high pressure center. And we looked at a real life example of a satellite images of sea surface temperatures, and we saw how these actually can spin off. Here's that cooler water trapping warm water, here's that warm water trapping cool water. But really this is just real life examples of these pressure systems that we've been exploring since we started talking about ocean circulation. And we sort of left it as, yes, the cold water can get trapped by warm water, yes, warm water can get trapped by cold water, and this makes us sort of call them, because of the temperature of the water being relatively either warm or cool at the center of the system, we can call it a warm core or a cold core eddy. But today we're going to explore we're going to complete the picture of these eddies. Okay, so really more to the root of why that's cold core and why it's warm core, and what is the significance of that. And really it comes from, so how do these systems exist, right? We know that we have pressure gradient, we have a high and a low pressure, and that causes flow from high to low, right? And with the high pressure centers, the flow is away from the center, and because it's deflected to the right this way, deflected this way, to the right this way, going to the left, we get a clockwise rotating system. And we know that the opposite happens with a low pressure center, where we have high pressures on the outside, so the flow is initially towards the center of the system, and once the rotation gets in, once geostrophic flow balances that, we get a counterclockwise rotation. So how come this mound of water, right, which is obviously exaggerated in the cartoons that I show you, but this high pressure center, how come it doesn't just flow out and we reach equilibrium and just become a flat surface? Why doesn't it just peter out? Why does it spin up into this? We know Coriolis is what causes it to deflect and to spin, but why doesn't it just peter out and that's it? So if we ever have the chance to have these high pressure, the high pressure around low, or low pressures around a high, why don't they just level off and peter out? What sustains them as a pressure system that will keep rotating and moving along? And so in order to do that, we have to kind of take all the definitions and the mechanisms that set up these systems one step further. And so now, really, for the first time, aside from the giant eddy that makes up an ocean jeer, we're going to talk about, for the first time, putting these systems in the ocean. So many different things can cause these systems to spin up in the ocean, like small-scale ocean weather events, just like high pressure system moving along over land that brings rain, or low pressure clashing with a high to cause thunderstorms, or just like a hurricane or a tornado. These things happen, but in the water. So we know, again, the high pressure system and a low pressure center system, we know that the flow goes from high to low. We know that it initially is deflected to the right, all the way around this thing, which causes it to rotate this way. But it doesn't just barely deflect to the right, it's that initial water. It's that initial flow that deflects a little bit to the right. Now that flow is now directed this way, and that water directed this way is deflected a little bit to the right, and that water is now deflected a little bit to the right. And the fact of the matter is that it just continues to wrap around like this, right? So that water is continually moving away from the center, but because of that continual deflection to the right, it's driving the system in a rotation this way, but it's continually deflecting to the right, and that's pushing water that's continually deflected to the right a little more, a little more, a little more, until it's redirected back at the center. Right? So if the water is constantly moving this way from every point outward, from every point from the center, then the thing is still rotating this way, but it's also reinforcing the high pressure center. The water's flowing out, wrapping around, reinforcing the high pressure center. Okay, so now let's look at a cross section. Let's put this high pressure center in the ocean. Okay. Right, so I just put these arrows in here to depict that the net transport of water at the very surface of this system is towards the center, continually maintaining that high, right? So if we look at that as a cross section in the ocean, right, the flow is initially away and away from the center, but as it rotates in this fashion and comes back to the center, the flow at the surface of the system is continually towards the center. Right? Now, if it just continually went towards the center and never went anywhere else, then this pile of water would just get higher and higher and higher, right? But it can't do that. Eventually, gravity overcomes the force of the system, and it has to go downward, right? So this everywhere on the surface of this system, so if we could picture this from above, everywhere on this system, the water is coming towards the center and sinking. So if the water is sinking from the top down and continually flowing this way, inevitably, though, there's going to be a pumping action down this way, right? So the flow is away from the center, This whole thing is rotating this way, right, clockwise. But in the surface, the water is always moving towards the center to maintain this high, and then sinking because of gravity. And even though it's doing this, it's also pumping down, and its overall effect is to push the thermocline down. Okay, so if we have warm water from the surface continually pushing the thermocline down, it's pushing warm water down, then the whole center of this thing is essentially a warm core, right? It's all warm water from the surface. Okay, and this action is the reverse of upwelling, and we call it downwelling, right? But the overall effect is to depress the thermocline. Now let's look at the cold core. It's the same dynamics, but in the opposite direction, right? We know that in the low pressure center, the flow is always away from the outside towards the low, away from the outside towards the low, and it starts to deflect towards the right and towards the right, and it makes this system continually spin in a counterclockwise, right? But it's the same as the warm core, but in the opposite direction. Okay, it pushes water that's deflected to the right, pushes water that's deflected a little more to the right, and a little more to the right, and a little more to the right, until eventually its net transport at the surface only, right? So we're looking only here at the surface of this system, is always transported towards the outside of the system. And what does that do? It continually maintains these highs, this high pressure on the outside of the system. So if we look at the cross section in the ocean, right? High pressure here, and it flows towards the center initially, right? But in order to maintain that, it's continually spinning this way, but redirecting surface water towards the outside to maintain these two high points, these two high pressure points. And again, they can't continually go up and up and up and build these piles of water higher and higher and higher. Eventually they have to sink and rotate in, sink and rotate in. But if at this surface water's continually pumping away, right? If here at the top of this high pressure center we have a convergence, here we have a what? We have a divergence, right? So the water's diverging away. And this would just continually get lower and lower and lower, and these would get higher and higher and higher, unless what? Water was replaced from below, right? So if water's pumping up from below, we have this motion going, and this motion going, right? But it also effectively pumps water up from below, okay? So this motion constantly pumps water up from below and sucks the thermocline up, shallower. Okay, so it's the opposite effect, a raised thermocline. So this pumps cold water from the deep upwards towards the center of this eddy. And since we're pumping cold water up, hence the name cold core eddy. But what also happens when we pump water up from the deep ocean into the surface ocean, we bring up nutrients, we bring up carbon dioxide, we bring up oxygen, all the things that make the food web run up here, and we get phytoplankton bloom, we get primary productivity and phytoplankton blooms, and so on and so forth in the food chain, right? And so here's a real life satellite example of how of an eddy spinning up, pumping water up. You can see pumping water up in the center and bringing up nutrients with it. You can see a smaller one over here. This looks like a big one that petered out, right? This looks like a big one that's starting to peter out, and here's one that's fresh and working hard to pump nutrients up from the deep ocean to cause a phytoplankton bloom. And these things can be caused by a lot of things. So they can be caused by water passing each other, just like the Gulf Stream and the northern current coming down along the eastern United States. They could be caused by a passing atmospheric storm, like if a low pressure system's going this way and a high pressure system's going this way in the atmosphere, it can cause these pressure differences, the pressure gradients in the ocean, strong enough to cause these kinds of things. Something really strong, like a hurricane, can cause these kinds of things. It just, anything that causes a gigantic pressure gradient, where you have a high and a low set up either at the center or at the outsides, we get one of these eddies that we've learned so much about. Okay, thanks for joining me. See you next lesson.